you're here, would you raise your hand? All right, well then we'll just adapt on the fly. So first off, I'd like to thank our host, Intuit, for hosting us here again tonight. And,
welcome. So those who haven't had a chance to meet before, welcome to Intuit. This is our third time hosting, I think the second in the last few months. And I just wanted to thank you all for coming here and spending some time with us. Just a little bit of background. My name is, like I said, is Chris Jaco. I help lead our data sciences and analytics team here at Intuit. And we believe that data is actually going to be the thing that's going to help us transform this company to become a world-class innovator. And so it's the technology and tools that will help us get there, but more importantly, I think it's the knowledge of folks in a community like this who can help us get to that. So we appreciate you having us host, and we hope to do it again in the future. And with that, I will turn it back to Joe.
Thank you. And our other sponsor tonight is Revolution Analytics, my employer, who picked up the pizza tab one more time. So now, as is our custom, is there anyone who has any other announcement? Maybe somebody who's hiring or someone who's looking for work? Is there anybody that would like to say anything? Okay, so then here's how it's going to work. The first speaker has a 20-minute slot, and the rest are 12-minute lightning talks. So Nicholas, our co-organizer here, will be keeping the times. So he'll give you the speakers 5 minutes, 2 minutes, and then you're off. So the way to do this efficiently, since we like to change up, people are going to use their own laptops for the most part. So as the next person is setting up, you can answer questions. Then we very much appreciate it if all the speakers would remain afterwards and answer questions at the end of the evening. There were some T-shirts here for the speakers. So please, the idea was, and I think we have enough, very appreciate you coming. And Tyler, so take it away.
So I'm a PhD candidate at UC Riverside, and I'm going to talk about my research on drug discovery with R. And the main question that I'm working on is related to trying to figure out how effective drugs that we're already using interact with the human body, and then look for patterns there and see if we can apply those same patterns to discover new drugs. And as a conservative estimate, there's been about 500,000 published studies that are looking at different aspects of how small molecule drugs work in the human body. And all of these are different experiments that are testing small molecules in different living systems and seeing how they behave. And in my research, I'm working on a software tool. It's an R language package that is for systematically analyzing these data and looking for patterns. And then hopefully using those patterns to then develop new treatments for human disease. So for those of you that aren't biologists, I'm just going to kind of explain this diagram on the slide is a general idea of what these kind of bioactivity experiments that I'm analyzing look like. And you generally have a small molecule of some kind. This is caffeine, for example. And the question is in the body, what of our natural molecules, proteins mostly, is it interacting with to cause the effect that it causes? And in this case, so we have this question mark, does it interact with that protein or that protein? And a protein is basically you can think of it as a small molecular machine that does something in your body as part of an important system. And proteins are often divided up into what we call domains, which are like the small functional parts of the protein that do different things. And most often, when a small molecule is having a drug-like effect in your body, it's because it's binding to a specific domain on a specific protein and altering how that protein functions. So the goal in drug discovery is generally to reduce the drug search space, because there's about 40 million small molecule compounds that have been identified or made in the laboratory that are potential drugs. And if you're going to have a certain disease or a certain pathway that you're trying to target, 40 million is too many to test in the lab. And with those 40 million compounds, there's maybe over 20,000 genes in the human genome that produce proteins, and then if you were to compare all those possible interactions, that's over 1 trillion combinations. So it's too much to test in the lab, and we'd like to use some data analysis to predict which ones would be the most effective possible combinations to test. So we want to leverage the existing experimental data to prioritize the search space and looking at patterns of activity in existing drugs, then identify which of those 40 million compounds have a high likelihood of being effective drugs, and then go to the next step to actually test them in the lab and eventually in living organisms. So a common question when you look at a small molecule drug is how many targets is it active against? Traditionally, people you would say that you want a drug that's active only against one target, because by being active against that one target, it has a specific biological effect, and it's not active against anything else that might cause an adverse effect. So I'll show you that, surprisingly though, with some of our existing drugs, they don't seem to work that way. They seem to be active against a lot of things, and yet not cause significant adverse effects. So the question that comes up from that is, these successful drugs that we're already using, do they tend to be active against just one target in the human body? Many different targets that are within the same pathway or system in the body, or active against many different systems? And one thing to consider when thinking about that question is the aspect of biological robustness. And this is a diagram of one way of thinking about biological systems. Most of the systems in your body use feedback in some way to automatically adjust how they're operating. So if they're damaged in some way, they'll compensate and continue functioning. And you can think of that sort of like a thermostat in your house. If you're heating the house and you crack the window and let more cold air in, the thermostat will adjust and automatically run the heater more, so the temperature will be the same. And this is a problem in drug discovery, because if you affect a system, in most cases, the body will compensate and you won't have any effect at all. So predicted interaction in the computer might actually do nothing in real life. Norbert Wiener is a mathematician that in the 1940s first formalized the mathematics that we now use for studying these systems. And when you look at it this way as a feedback system with input and output, if you have a drug that attacks one system, like one part of the system right here, then the feedback will compensate. But if you have a drug that affects 2 points, then maybe you can affect the feedback signal as well and exhibit a stronger overall effect. So that's the theory. So the question is, do existing drugs tend to do this, where they're attacking in multiple places, or do they just attack in one place and work anyway? And in order to address this question, I'm looking at existing published data from bioassay experiments. And these bioassay experiments are, like I said, studies where you have one protein generally in mind, and then you test a large number, often tens of thousands of different small molecules, against that protein to see if it binds to it. And then you get the data in the end in a computer-readable way. So all these experiments can be summarized like this. It's kind of a matrix where you have, the structure of every small molecule that was tested. And for a particular protein target, you say that it's either active or inactive. And the person designing the experiment needs to decide what sort of a cutoff value is going to be called active or inactive, and then so that it can be simplified in that way. And these experiments are done in automated, where you do tens of thousands of compounds, and they're done on a robot with plates like you see in the picture here. So the problem is when you have all this data that's already been published, hundreds of thousands of these experiments, they were all done by different labs and different experimental designs, and it's hard to systematically look at them all. So it's really a big mess of data. And there's a lot of mathematical problems in order to make sense of it. And but that's part of the novelty with what I'm doing here is that I am taking all of the published data and looking at it all simultaneously at once. And one of the problems with this data is that it's sparse. So if you have all the protein targets in the human body against this bottom axis and all the different 40 million small molecules that we know up here, and you can see which ones have been tested to be active against which, and you say this is active, that's an inactive combination, most of your values are going to be just empty. So just most of them haven't been tested, but yet we want to make meaningful predictions anyway, despite the lack of data. And then another problem here is noise. There's what's the true positive and false positive rate, because in these data there are a lot of false and true positives, and the rates are different for different types of experiments. So you have to keep track of how the experiment was performed, and then based on that, how accurate and how much confidence can you have in the result. So in order to address these problems, I'm going to talk about a software package. It's an R language package that I released. And so the lab I work in, we currently have 5 R packages for drug discovery, and they're published in the Bioconductor project. I don't know how many of you are familiar with that, but it's similar to CRAN, but it's peer-reviewed, and it's only for biology-related software packages. And this particular package I'm talking about is called Bioassay R, and it's a package specifically designed for analyzing the data from these bioassay experiments systematically when you have a large number of experiments. And the software, this is an overview of how the software is designed. It has 3 main data objects here. You have the bioassays themselves, which are just the scores of each compound that was tested against a single target, and then all of those are loaded into a SQL database. And then when you can, based on what kind of biological question you're asking, you can pull out of the SQL database a bioassay set, which has just the protein targets or just the small molecules that you're interested in. So it's a subset of the SQL database that's in a matrix. You can see where it's the compounds against the different assay experiments and the scores in the matrix, and then all of the extra metadata for each experiment. And when you have this bioassay set object, you can then take that data and you can summarize it into a sparse matrix, which the sparse matrix is a way of sort of compressing the data, so you're only storing the combinations that have been tested in memory rather than the entire all possible combinations. And in this case, often different assay experiments are actually against the same target. So in that case, you want to collapse the scores from multiple experiments into a single one that summarizes the information from both. So you have, here is a matrix where you have all of these different small molecule compounds, and then on the other axis, you have all the different protein targets in the human body that have been tested. So from this matrix, you can then do some statistics on the different compounds to see how they perform. And this is an example of where you put the matrix in and you get these different, for each small molecule compound, you can calculate selectivity, domain selectivity, and module selectivity. And I'll explain what those mean. Selectivity is how many different protein targets is it active against. Like I was saying before, if it's active against one protein target in the body, then it's a selectivity of 1, and so on. So in this case, a single compound may have been tested in 8 different assays against 8 different targets, and it was active against 4 of them, and inactive against 4 of them, and we say the target selectivity is 4. One issue here is that a lot of the different protein targets in the human body are substantially similar. Maybe there's just a slight difference between them, but they're so similar that you might expect the same drug to interact with both of them. And in that case, say these 2 share a common domain, which is a subgroup of that protein that has a similar function. In this case, we define domain selectivity, where we just collapse those together and say that the domain selectivity is 3. So we know that it's active against at least 3 different proteins that are quite different. So that's a more conservative estimate of how many possible targets a small molecule drug might be active against. So let me show some of the preliminary data that I've found using this software. This is looking at the domain selectivity of 289,000 randomly chosen compounds. These are non-drugs, so these are just random small molecules. And the question is, what percentage of them are active against one target, what percentage of them are active against two targets, and so on. And you can see it's most common for them to be active against one target, about 35% are, and higher and higher number of targets are progressively less likely, and it sort of looks like exponential decay. There doesn't seem to be a strong relationship between whether they'll be active against one or another. But I'm going to put in alongside this the FDA-approved drugs, which are already in widespread use. And these are 701 FDA-approved drugs that have enough screening data to estimate how many targets they'll be active against. And you can see here that it doesn't fall off so steeply. There seems to be a greater number of a greater percentage of these FDA-approved drugs that are active against more targets than the random compounds. And so the random compounds have a median value of being active against 2 targets, whereas the FDA-approved drugs have a median activity of being active against 6. So that raises the question, are these drugs actually that are working, is it important that they're active against a large number of targets for them to work, or is that just a random chance or artifact of the data? And so in order to look into that question, I'm doing a target network analysis, which is looking to see what is the biological relationship between those different targets when a small molecule drug is active against multiple targets. Do they tend to be just random, active against a lot of different proteins in the body, or do they tend to have some kind of close functional relationship? Or if the same drug is targeting 2 things in your body, are those things in the same system or 2 widely different systems? And so here's an example of what I found. The average non-drug, just a random compound, if you make a network of the things it's active against, you say on average it'll be active against 4 different targets in the human body here, but that none of them would be tend to be in the same pathway. So by pathway I mean the same subsystem in the body that does a certain thing. Like you have a pathway that metabolizes glucose, a pathway that metabolizes fat. And in this case, a random compound, if it targets multiple things, they don't tend to be in the same pathway. But if we take a typical FDA-approved drug, it tends to be active against 9 targets on average, but 4 of them will typically be within the same pathway, which is somewhat unlikely to happen by random chance, which seems like for some of these drugs, it suggests that it may be part of the mechanism of activity of the drug that is targeting multiple things in the same pathway. And this next graph is a little hard to understand, but the main thing that it's showing here is that there seems to be 2 different types of FDA-approved drugs. Some of them are really just active against a small number of targets, maybe only 1 target, and those are usually, if it's active against a small number, they're usually in different pathways. But there's some that are active against a large number of targets, and all of those tend to be, or a large number of those tend to be in the same pathway together. So it seems like there's a certain class of drugs where the mechanism is that it has to target a bunch of related targets. So you can see the FDA-approved drugs are the red bars here, and here is the number of active targets on the bottom, and the percent, and the number of those that are in the same pathway. So you can see, like, for drugs that have 11 active targets, around 3 or so tend to be in the same pathway. And you can see the red bars start to get higher than the gray bars as you get into more active targets. So the red bars means that if you have one of the drugs that are active against 16 targets, a much higher percentage of those of the FDA-approved drugs, their targets are in the same pathway as compared to just random small molecules. So this is just showing the sparse matrix visually in a heat map. So you can see that the small molecules are over here, and the proteins are here, and there's red wherever there's activity. And these are grouped together according to structural similarity. So this teal group, for example, here, is all of the steroid-derived hormones like progesterone, testosterone, estrogen, they're cholesterol-derived hormones. And you can see that there's kind of a, I don't know how good the projector is, you can see there's a bright line there. And progesterone, for example, seems to be active against 327 different targets in these assay experiments. Whereas this succinic acid, which is a small molecule that is part of the citric acid cycle for metabolizing energy from food, it's only active against one target in the experiments we've seen. So you can see there's certain classes of structured small molecules that generally in their mechanism are active against a lot of targets. And so that's a potential thing that we could look at for discovering new drugs, is rather than looking at a single target, look at things that have this pattern of activity similar to these existing drugs, where they're targeting a large number of targets that have a functional related relationship. So the next step in this project that I'm working on is to sort of summarize these data using a statistical method. So we're summarizing it to create a Bayesian drug effectiveness score, which says for a specific target or a specific pathway that you're trying to discover a drug against, of all of the data we have, you could calculate the probability that each of these compounds is likely to be a drug and take the highest probability ones and test those in the lab. And so that's where I'm hoping to develop. I'm working on developing that now, so if anyone in the audience is a statistician and that sounds interesting to you and you want to talk about that, you should come and talk to me afterwards. And I'm also working with Andrew here, and we're planning on eventually starting a startup company that would predict small molecule drugs and then provide those predictions to the pharmaceutical industry to accelerate their lab discovery process. So last, I'd like to thank my PhD advisor, Thomas Sturkey, and my lab mates, Eddie and Anna, and the bioengineering program at UC Riverside, and the National Science Foundation, who provided funding for this research.
So we want to have a look at some of the R code for this. It's in the package, and are the examples accessible?
Yes, so the bioassay R package is in Bioconductor. You can download it on the bioconductor.org website, and there's a PDF vignette that talks you through some examples of how to use it for different things. And it's also on GitHub. So the PDF shows some examples of different drug discovery experiments you might want to use it for, and then you can run the code line by line and see how that works.
Thank you. One more question while Antonio, you set up?
Yeah.
So in your multiple targets analysis for approved drugs, most drugs that are on the market are prodrugs. In other words, they're first metabolized and then they actually hit their target.
Mm-hmm.
So it really depends which part of the CYP pathway they need to metabolize to really determine if they're active. So it seems like it might not be a real characterization to look at what they're hitting
Directly.
And also, usually the one that's marketed is not the one that's published in the screen because they've been re-engineered in medicinal chemistry to be more specific and also to make sure that they're metabolized properly.
Mm-hmm. Well, the data I have here is just the ones where the compound is already on the market. But I think that would be a good thing to look at in the case of the prodrugs, look at the actual active molecule instead of the prodrug compound.
Quick question.
Yeah.
It looks like he's still setting up. How about the FDA also incorporating this information when they approve drugs? Sounds great.
So the question was, how about the FDA incorporating this information?
Well, I think this is mostly for early on in the process to eliminate things that are likely to have adverse effects. But by the time you get to FDA approval, you're going to have a lot more real-world experimental data where you would say, is it actually toxic in the real world or not? So hopefully we avoid trying to get things through FDA approval that end up being toxic. But this data, because it's like a probability of it being toxic or not, it's not as meaningful as the the hard experimental data that the FDA requires when you're actually in the approval process.
Thank you. So, Antonio, please.
Hello? Can you hear me?
Yes.
So I have a little self-contained topic here. It's this is a screenshot. Actually, it's not actually my blog. Or it's very different aspect ratio. No, that's our country. It's a little wide there. And so you can find the whole Piccolboni.info where my blog sits. So the motivation for this was this New York Times article. Sometimes I read an article and I get angry, and so I do statistics. If I want to make money, I do. So this is the map. It's part of the column called Upshot that mixes data and journalism, sometimes with different results. And it's supposed to be a map, and this probably is a map of where life is hardest in the United States. Guess what? Is the green hard or the orange? The orange. And so the map is obtained combining 6 observable: education, median household income, unemployment rate, disability rate, life expectancy, and obesity. And then they need to summarize this to a single real number, and so they take the ranks for each variable and average the ranks. So I may be kind of methodologically sensitive, but even the regular New York Times reader, they complain about the choice of variables. Why this? Why obesity? Obesity is not a recognized disease. It's related to diseases, and we know that, but why not cancer? Why not mortality, all causes? You know, there's already life expectancy, like why double it up with obesity? And another reader says, why median income? You know, median income, it's not comparable between counties, you know, and he has a point. I found the county up here, strange, it should pop up some detail, but at the entrance of Yellowstone with 50K, it puts, and of course, in combination with the other variables, put that county at place 54 in the ranking, and with about the same amount of money here near Chicago, there's a county that's ranked 2000. So 50K don't mean the same if you are a government employee, you know, like a biologist working in Yellowstone versus somebody trying to scrape in Chicago with the kids. So that's the first thing. The other, the combination, many of your statisticians say, can you average ranks like that? You know, and it looks okay. There's no weights, no particular choices, but it is somewhat arbitrary because you are trading ranks in one thing that's in one unit of measure with a rank in the other. So like the range of median incomes changes by about 85K. The range of life expectancies changes covers about 11 years. So when you trade, say you're averaging ranks, I'm taking a really big change here, right? But it's like saying you're trading 85K with 11 years of life. I'm not me. Right, and so, and I just had to test, you know, did they choose these variables? Did they do the aggregation so that they could get certain results? Actually, I don't believe so. The article is a little rambling, doesn't have a big message at the end that we should do this, we should do that. So I don't think there was any intention, but they just went by the seat of their pants and did this analysis. So it's impossible for me to respond also because it's the New York Times, so I don't have the ambition to respond to the New York Times. But I wanted to do an analysis completely different. So I took a weekend, instead of being a good family person, I did an analysis the way I like it. So the first I found lots of data. Second, I discarded almost none of it. And because also I work in big data, so if I discard data, I kind of jeopardizing the other part of my career. And the other thing, I try to do an analysis where there are no choices, or very few and not particularly questionable. And at the end, we end up with 10 maps, not one, that show some diversity. Instead of just saying, oh, we have 6 variables, we pick them up without telling you how, and they're all correlated, I show you 10 different ways of looking at 10 different maps of the United States that are related with the census data. So the methodology here is relatively straightforward. You go to the census.gov website, you find a bunch of zip files. There's data at different levels. I focused on counties, level data. And then you unzip those, you get Excel files, and then you have like 50 minutes of desperation. What do I do with the Excel files? I don't even have one Microsoft license. But there's another called Excel to CSV that almost saves the day because it creates almost CSV files, which are actually concatenation of CSV files, one per sheet in the Excel file, because those are multi-sheet Excel files. And those are all the same length, you just do split and you get card-carrying CSV files that can go into R very easily. From now on, all the code is on GitHub and also in the paper. And if you want the derived data, remind me, because that's on my hardware. No, it's not available. The original data is on Census website. And then there's the data cleaning. The data cleaning is not so interesting, but a little interesting is what do you do with 6,000 variables? You're not a demographer, so to understand one variable, I had to read for at least 10 minutes, you know. And so you try to do reasonable things, and you experiment with a sampling of variables. You know, see, okay, I have a heuristic to drop some variables, and I'm going to look at the sampling of variables and see if it works. That's the best you can do in a weekend. So here, there's lots of columns that have data, and lots of columns that assist the other columns. They have metadata. They say why that cell is empty, why, you know, the census guy with fever, you know, couldn't go, and or, you know, some crazy guy beat him up because he was asking too many questions or something. I don't want to analyze that, so I did this little test. Are there at least 50 distinct values? So it's good. That seems to work all right from eyeballing a sample. And then you can put everything in data frame, with just cbind, it's all the same number of rows and order. And then there's also redundant columns because it's the name of the counties, one of the categorical columns, don't ask me why. And then there's rows for the states, this is county focused, okay, and then this probably is useless. And then there's another separate piece of information which for every column gives some explanation. There's some a little extended text and some annotations that are kind of hard to use. And so, but we'll use it, we'll use the extended text in a moment. So what we have now is a 3,000 by 6,000 matrix, a little bigger, and it contains things like private non-farm annual payrolls, economic data, or non-federal positions inactive as of December 31st, 2006. So there's dates in it, and the temporal dimension is a limitation of this analysis. And there's lots of different units, area of farms, dollars made, years of age, counts of people, and also they're aggregating different ways. There's average, medians, blah, 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 what you do. I was hoping, okay, I put it in some statistical thing and not have to think about it, but unfortunately, it didn't work right away, and I realized that the size of the county was too much of a nuisance factor. So the only kind of semi-intelligent step here was to find the columns that are absolute numbers and divide them by an estimate of the population in that county. So that was done by looking at simple keywords in the extended description. At this point, I applied PCA, but the series of eigenvalues was decreased very slowly. If you're stupid, always look as a agnostic so that they will save you from looking even more stupid. So I thought, what do I do? I don't want to do clustering. I want to do something that will show the overlapping dynamic, you know, of life of the census in the United States. And so I thought, random forests are general, and they can do all sorts of types of inputs and whatnot, but they don't work only for classification and regression. I was wrong. They work also for unsupervised learning, and you can apply to this data. What you get is a proximity matrix. And from that, you apply dimensionality reduction because the proximity matrix is 3,000 by 3,000, so it doesn't help that much. And the dimensionality reduction goes through PCA again. You can check the eigenvalues. They go down pretty quickly. And then you look at pairs of variables plotted against each other. You see those bananas and S's. Those are variables that are uncorrelated, but unfortunately, they have some dependency. So that's supposedly not good. So you can use the PCA as a starting point for the independent component analysis, which is actually, but that's optional. So essentially throw away the PCA and start with the ICA after the random foresting, and you get this other set of pairs. I thought this is good enough for me. It's getting to the end of the day, so I gotta plot something. And so you get a map package for data and then ggplot to plot. And you get maps like this. And when I saw the first, I said, yeah, those are the Great Plains. Statistics invented discover the Great Plains. But not all maps are that obviously interpretable. So I used two methods or suggestions for interpretation for the early paper about the multidimensional scaling, which is find extreme cases. Extreme sounds a little derogatory, so I call them champions. So countries that represent the extreme in each variable independently, and look for original variables that correlate or anti-correlate with the reduced variables, whatever way you reduce them. In this case, they're independent components. And 2 minutes to get to these maps. So the final product of this article are these 10 maps. The champions are up here. I like to click on this one because Dublin, North Carolina is distinguished because it has the largest number of hogs in the country among all other countries. And hogs are not in the census data, so that was surprising. I wrote also a turbo text, and that really will not stand the test of time. I'm sorry I did it, and that's absolutely no rigorous like the titles. Just don't read those, I will erase them soon. And so we have this map. The red is somewhat related to manufacturing activity. See the little spot in the different manufacturing sectors. And there is this component that seems to be in the Ohio Valley and a little bit of Appalachia, lower Mississippi Valley, plus a little bit of South Dakota where there's lots of Indian reservations. I don't know what the relation is. And we have this other one that I will kind of forget what the name is exactly, but it looks the most like the New York Times map. So maybe it's a map of money. And then we have this, which is these interesting circles around the large urban areas. You see Dallas, Atlanta, the big splotch around Washington, D.C., and Minneapolis and Paul up there. And then we have this one, which is something else, in the east-west divide. It has to do with minorities if you look at the descriptive variables. And going faster and faster. Then we have the deep south here. No, sorry, this is the map of coastal cities. And the last one, the upper Midwest. And I'm done. Piccolboni.info.
Repeat, please.
Google me, you go there even if you don't want to.
And we'll,
At least send any comments and we'll make it better.
and we'll have a link from the meetup site.
All right.
Was this done in knitter or R Markdown or?
R Markdown.
Okay.
Yeah. I'm sorry I didn't mention all the packages, Xtemp for the tables, and thank you to all the guys who provided that software.
Dennis, are you ready to set up?
Yes.
Another question? Well, yes.
So just out of curiosity, what is ICA?
Independent compliant analysis.
Okay, thank you. That's what I thought. I just had never heard of it before.
Yes?
When you said you removed very little data, were you talking about Alaska and Hawaii? Or?
Say that again, please.
When you said you removed a little data, was that Alaska and Hawaii?
The data that you removed.
No, that's there were a few countries that dropped off because they had funky names, so at least people spelled them differently. And Alaska and Hawaii are not in that geographical data. I actually never thought about it. I'm very sorry for people living out in the continental states because they disappeared and I noticed only right now. So that's something to look in as a case.
If you normalize by population, do you consider plotting on a map for the areas of the counties with scale from the country?
Oh, it's called like that's a separate, maybe one day.
Is there an easy way to do that?
Cartogram, I don't think there's a package for that. We would have to do farm it. There is? Okay. Scape toes.
Scape toes.
Thank you.
All right, thank you. So Antonio will be around. So Dennis, please, take it away.
Okay, can you hear me? Okay. Oh. I have a shiny badge. I found it at a street art fair, and I just had to have it. So it's dynamic, like shiny. It changes colors. So I'm going to show you this example of using shiny. How many people here have used shiny, at least going through a tutorial or something? Yeah. Quite a few of you. Okay. And I do have this code on GitHub, and I will show that reference again at the end. So this is what the data looks like. It's about 1.8 million records. Very simple structure. It comes from the Social Security Administration, the cards that were filled in to register for it. And it only has people who were born in the U.S., no naturalized citizens. But year, sex, name, N is number of occurrences, and proportion. So in 1880, there were 7,065 baby girls named Mary who were registered, eventually registered. Social Security system didn't start till 1937, but then they had others born earlier. Proportion is based on the number of people within that gender. You can see there's quite a difference between females and males. There's more females, not because there are more females in the system, it's because there's more variety in the female names over the years. And if you add up all the M's there, it's about 333 million total people represented. That's sort of, yeah. First, I'll do some acknowledgments. Shiny package was offered by the RStudio team. It's maintained by Winston Chang and Hadley Wickham. Baby names R package was written by Hadley Wickham, and that just allows the data set to be accessed easily. And he also filtered it so that you had to have it, N has to be at least 5 for any 1 year and any 1 name. Takes out a bunch of lower occurrences. And then this idea really came from Garrett Groleman, who's the master trainer at RStudio, and he did a tutorial on Shiny at the useR conference this summer, and so he just got started with this, and I picked it up and took it a lot farther. And then there's all this junk from the Social Security Administration. Basically, it's saying take the data as is. It's messy. There's misspellings and everything. So I'm using, this is actually the Shiny app itself, one tab, the acknowledgements tab, and I'm using the nav bar page mechanism, which I find is really good for presenting information in a condensed way. So I click on profiles. Here we've got a sidebar and 2 plots, and one of them is, let's see if, well, okay, I'll work with that. So we've got 2 time series profiles up here. They're representing Bonnie and Clyde. Celebrated criminals from the early 20s, went around robbing banks, died of violent death. Okay, but this is showing percent within gender against year. It also shows, okay, Bonnie's peak, 1942, total namings, 322,000. So total namings is basically the area under the curve. Same thing for Clyde, and a different spot down here. Show that a little better. Okay, difference plot is helpful for seeing the differences between those two curves. It was a little non-trivial. It's not just a matter of subtracting those. I had to make sure there were no zeros, no missing years. And I started using the geom area capability in ggplot for that, and it turns out that didn't work. So I used geom ribbon instead. So this is actually written with two different geom ribbon statements. And geom area is actually a special case of geom ribbon. And yeah. And so if we move along, see we've got more common names, Mary and John. So when I'm typing that, because it's reactive, if you're just typing faster than the delay in the listener in Shiny, then it's not going to try to update your screen. So type fast. So Mary and John have been declining over the years. And here's the difference plot. So I also built in here a smoother. So here's a local weighted regression. So this is weighted quadratic local regressions that smooths that, can change the span parameter and generalize it more, make it smoother, make it smaller, and then you end up getting more of the high frequency variation in there. I won't show the high pass filter is almost the same. Okay, now there is also the list view. And there I'm actually converting the data frame to a data.table, just because I wanted to experiment with that. And so here we've got some input widgets again on the top. They can be collated with the output, so that's fine. And then, so we can select things, select the males instead of the females. Changes pretty quickly. And really the most interesting thing here is aggregate by name. And so what we see here is overall sometimes you have to hit the percent things again. It's a little tricky. Data.table does things in place, and sometimes it's a little hard using that within ggplot. But this shows overall, over all the years, Mary had the highest average percentage. However, a lot of that was concentrated on the early years. So if we change this bar, say 1985 on, I'm going to click again here. It's Jessica, Ashley, and Amanda are the highest. This thing's fun to play with. Okay, say we wanted to compare, say Amanda and Emily are similar there. Say we want to put them in here. Amanda, they were similar at one point, but you can see the variations there. And just wanted to show something else of interest. Okay, we got to change Elvis back to male. And we're going to make Winston male too. Okay. Elvis became popular right about here. Okay, so a lot of people started naming their kids after Elvis. He died in 1977, sadly, and so a lot of people named him there too, but actually also a year before also. Winston, the early 40s, a lot of Americans admired Winston Churchill. Okay, so those are the kinds of things that you can play with. If you got Winston up there, you got to put Hadley also, because he's there. Not too many Hadleys, but if you change Hadley to female, Look at all those. Look at all these. So I think that means we're going to have great women engineers in R in a few years. And then just some final points. So the features that I've covered are reactivity, selection, comparison, time series smoothing, graph and table views, and you can use a compact, there's some tools to make compact displays so you're not wasting a lot of white space on the screen. What I'm going to work on more is selection and display options, error trapping. Sometimes it's debugging and error trapping is a little difficult in Shiny because it does so much low-level automatically. And there's a really interesting machine learning problem here with classifying time series. So I intend to play with that. Again, here's my GitHub account, email address, and I'm looking for an opportunity in data science. Thank you.
Dave, are you here? You can set up. Dave Ravisa. And we'll take a question while Dave's setting up.
How long did it take you to do this?
It was, I don't know, 60, 70 hours. So some of it was learning, do a lot faster next time. And more time, come see me later, we can type in some more names.
Any other questions?
Was the parents name also as a part of the data set to look into sort of like a network graph or social?
No, they're all independent, and it's first name only, no middle names or last names.
Okay.
There is a version of it that's for state also. I didn't look at that. It's broken out by state.
Thank you. Please, Nicole.
Thank you. Hi. Testing. You guys hear me?
Yes.
All right. So I'm Nicole White. I'm a data scientist in Neo4j. And I'll be talking today about how I use R and Neo4j together to manage and analyze highly connected data sets. So in a nutshell, this is my workflow day to day. At the very top, I'll have Neo4j, which is a graph database, as my data storage, data persistence solution. And then in the middle, I'll have RNeo4j, which is the R driver for Neo4j that allows you to connect to that database and query it and manipulate it, just like any of the R drivers would work. And then at the bottom, I'll have iGraph. Anyone here use iGraph before? Great. That's it's an R package for network analysis or graph algorithm analysis, and there's a few others, but this is what I personally use. So here I'll get into the data set I'll be using today, and hopefully this answers the question, what is Neo4j, what is a graph database? Doesn't show up quite right over there, but you can look over here. So a graph database, you can see that we have a few different types of nodes and a few different types of relationships, and the relationships are directed, and you pretty much semantically describe what's going on here. So I have a script that's running, not right now because I'm not on the internet, but a script, like every 30 seconds, it will grab tweets with hashtag #RStats and update this database with the information that it's found. And so I'll be collecting these tweets and updating this database, and all of these entities, both the nodes and relationships, can have an arbitrary amount of properties attached to them. We can have user, so the user node, for example, would have a username property on it. A tweet would have its date, its text and everything, a hashtag, its name. And so we see that we're storing users, which tweets they posted, if that retweet was a reply to another tweet, or if it's retweeted the tweet, if it's mentioned another user, if it has any hashtags tagging it. And so it's a pretty intricate data set. It's not something that I want to store in any type of table, either CSV or a SQL database. And I get all the classic database things that you would want, such as uniqueness constraints saying that there can only be one user with this username, and indexing, and all that good stuff. And quickly, I want to compare and contrast a little bit with a mathematical graph. And a mathematical graph doesn't really have a notion of node types and edge types. It's really just a collection of nodes that are possibly connected by an edge and possibly directed and possibly weighted like it is here. And if I want to do something that's a graph global operation, like a graph algorithm, or find the whatever centrality measure on every node in my graph, this is the data structure that I want to do that on, because all those algorithms are written for a graph that is like this. It's not something that I'd want to run on a graph database, because you don't want to ask any database a question that touches every single thing or observation or table or whatever. So I will use useR, a graph database really, of any graph database, to store an intricate data set like that, where we have different nodes, we have users, hashtags, tweets, and then I'll use, in the middle, again, RSiteCatalyst to ask for a subset from that database and infer or coerce, if you will, a mathematical graph out of that for the purposes of doing an exploratory analysis in R, and specifically iGraph. So here we see, I can think of several ways that I can infer a graph like this, a mathematical graph, out of my graph database. For example, I might want to look at something where each of these nodes is a user and an edge exists between them if they have tweeted the same hashtag, and it could be weighted by how many times they have done that. And when you have your data stored already in a graph database, it's really easy to infer that information out. It's just a few lines in our query language. So I'm going to just jump into our studio and we can mirror my display. Otherwise, we don't see anything. Okay, so to do this, hopefully you guys see this all right. The only libraries you need are iGraph and RSiteCatalyst to do something like this. So I have that data set. I have this data set already loaded, and it's already, I don't think I confirmed, started locally on my machine, and so I'm just going to go ahead and, what's that? Did I confirm? I think I confirmed this time. Alright, so anyway, so I have that database up and running, and I'm going to connect to it now. And so in the example I mentioned earlier, I want to look at a subset of my database where users are connected by an edge. If they tweet the same hashtag, and I'm going to weight that by how many times that's happened. And I can infer that information out with our query language cipher, which you can see right here. Beyond the match clause at the very top, it's pretty SQL-like, so if you've written SQL, it's pretty easy to get started with this. But this match clause at the very top is getting what I just said. It's really just users who posted a tweet that have been tagged by the same hashtag. So I'll go ahead and define that query. And then I can get that data out of my database using an RSiteCatalyst function cipher. We'll pass the graph object and that query to get that data out. And we see that we get this, what iGraph refers to as an edge list. So we have, if two users are in the same row, they'll be connected in our iGraph object by a weight in that third column. So we can use the iGraph graph data frame function, which takes an edge list just like that, and that will create an iGraph thing. And then we can real quickly visualize this subset that we've asked about from our database. Again, users that treat the same hashtag. So now I'm comfortable doing all of these graph global type questions, like find the betweenness centrality of every single node in my graph. And between this is how many times the node is on the shortest path. A pretty expensive operation that I wouldn't want to ask with a database. And you see things like data robot, how do you look up, so it's a fun way. I don't know what data robot is, so I'm not going to go check that out. It's pretty influential user, apparently. We can do fun things like, let's make the size of the node a function of its betweenness. And you can see, again, this could be thought of as an influence measure of some sort. And we can use iGraph again to run a clustering algorithm. This is the edge betweenness clustering algorithm of Curve and Newman, something or other that you can read out on your own time. But and then we can just do some real quick exploratory analysis of this subset that we've asked about from our graph database. So that was users connected by hashtag tweets. Now let's say I want to turn around and I want to look at a subgraph from a database where every node is a hashtag and these nodes are connected if they have been mentioned together in a tweet. And again, I'll weight it by how many times that's happened. So I just overwritten the query to be that, and I can again just use the same exact script to look at this different subset now. So now I have an edge list of hashtags weighted by how many times they've been mentioned together. And yeah, I can just use the same exact script. I'll load that edge list into an iGraph object and look at that. So it's a bit smaller, there's not as many hashtags as users, and so now I'm just analyzing the graph here. So we can look at the top hashtags by betweenness again. I've omitted R stats because it's on everything. So these are the next top ones. We have R data and statistics, which isn't too surprising. Again, we can visualize by betweenness as its size as a function of betweenness and run the same clustering algorithm and plot that. So I think it's just a cool way to use a graph database like Neo4j to manage your highly connected data sets that don't really fit into a table-like structure very easily, and then you can easily coerce these mathematical graphs out of your graph database and do these exploratory analyses in iGraph where you want to do, again, graph global operations, graph global questions. So that is my demo of that workflow, work process, which I do pretty often professionally at Neo4j with our data, because we store all of our data in our own database. Well, we'll make a next slide. Well, that's the repository for the R package. If you want to go check that out, I really like getting other reports. So definitely, if you do end up downloading it, let me know if you have an issue with it. I have a lot of documentation on my blog, which you can find on the GitHub repository if you look around. So yeah, that's all I have. Thank you.
Vince, are you here?
Yes, I am.
Please sit up.
Yeah.
At what point will your program break? If you had, say, 1 million, people or things, you have to kind of segment the graph, right? Do you know what the max size where it's just not runnable?
Most I've ever done on my personal machine, it's probably like 500,000.
Single core?
Whatever is the newest MacBook.
But you're threading it through one core, or are you doing like a kind of different column?
Just standard default RStudio,
Okay.
R 3.1.1.
I got you.
Yeah, most I've done is like 500,000. And, it'll scale as much as you pay for it to scale, so, yes.
Is it possible to do it in like near real time where I'm using like something like stream R package where it's constantly getting the tweets and it goes into Neo4j
Yeah, again, it'll be as fast as your machine allows it to be. I've only ever done offline analysis. The database is being dynamically updated, but as soon as I pull that information into R, it's static. It's just in my R memory. I've never done any real-time stuff. I'm sure it could be done. Again, it's the integration with R.
Thank you very much.
Muddling my way through technical issues. That's true. Or don't be gay. And yeah, I'll just extend this. All right, so first I'll just introduce myself. My name is Scopino. I actually am the lone Intuit presenter tonight. So I work on the Intuit SVG Global Marketing Analytics team. And just to give you an idea of some of the work that we do, some of the high-level projects that we have are things like multi-channel attribution, targeting, retargeting, and personalization. We have people who are building a data mart in our team, basically to gather data from places like AdLens, if you're familiar with paid search advertising, or display advertisers like X+1. So a lot of very high-level projects that we have here, and definitely a lot of interesting work. I was going to talk about multi-channel attribution today, but I did not find that that was a particularly interesting R topic necessarily, just because I ended up using the GBM package, which wasn't, I think, anything terribly novel compared to what some of the people have done here. So I actually decided to focus on one of the more mundane tasks of the job, which is web analytics. So if anybody has ever had the misfortune of having to pump out reports from RSiteCatalyst or Google Analytics, then you know it's a pain in the ass. And you wish that you could replicate that and pull thousands of lines at any given time. Unless, of course, you have some back-end database, but that's all being typed to. So anyway, I thought I'd talk about two packages that I really, really like in R, called RSiteCatalyst and RGoogleAnalytics. And I just provided a couple of links here. There's basically no slideshow presentation. I'm going to bring you through a live demo, and if it crashes, it crashes. If it doesn't, it doesn't. So without further ado, let's bring up our studio. Alright, maybe let's go through it like this. Sorry. The display mirror had worked. We didn't have these problems. So the first one is our Google Analytics, which I like a lot because this is great for people who are using a free version of GA, because this will actually give you not always totally unsampled data, but it will at least pull for you the most data that you possibly can. And if you have a premium version, then this is just a great alternative to actually pulling reports directly from Google Analytics. So again, this package is available on GitHub. I'm not sure if it's on CRAN. I know the RSiteCatalyst one is available on CRAN, but this one might just only be on GitHub at this point. I don't have the install stuff here, but from those links, it's all very straightforward. So I believe this is built on S4 classes. So it's sort of one of the latest and greatest packages out there in terms of that. So we start off by obviously calling the library and making a query object. And we'll provide our access token. So on the other screen, let me just pull this up. It'll open up a window here, and you'll start the OAuth playground. I'm not going to put that in front of you. Get your authorization token. that authorization token in. It accepts it, which is a miracle. And then I can start my Google Analytics objects. So I'll just call it GA. And I can pull all my different report suite profiles out of this. So you can see, for Intuit, we have a bunch of different global profiles, whether that's UK, India, Australia. This basically just gives you a quick view of all your properties and their IDs. So you might ask yourself, well, yeah, I know GA is painful, but why would I really want to do this? The cases where you would particularly want to do this, I find, is when you have a multitude of segments on your visitors, and you want to compare these segments. And that's a big pain in the butt to do on a regular basis, and pull it directly from GA. And even the GA Query Explorer limits you to 10,000 rows worth of data. This thing actually cheats that by sort of doing a paginated query. So it will just fire off multiple queries, picking up where the last one left off. So what I can do is define these segments here. So I have a site total, which is not really a segment at all. And I have a couple of other segments, like my SEO traffic, my direct traffic, or my online acquisition traffic, which is basically paid search. I can use regular expressions to define filters. And then sort of in this master query here, so I've started off with segment equals null. And then basically I can fill in those segments with something from the segments list, right? And loop through those different segments. So if we actually run this thing, you can see it actually gathering the results from each time that it loops through the query. Yeah, so I'm just binding together each one of these data frames that it's pulling within the loop. And then I use SQLDF, which I assume a lot of you have used, but that's one of my favorite things. So I have another table here. Google Analytics, it has its own Google Weeks, and as any company, you might have your own fiscal year. So I just do some matching there. SQLDF always runs super fast, especially on a small data set. And then I can write this table. Now you could use, go ahead. Oh, sorry. 5 minutes. All right, cool. Anyway, you can either write this to a text file or you can deploy it in Shiny, as some people have. Since we have Tableau with Intuit, I just wrote it to a flat text file. You could certainly store it in a database or wherever it is you want to put it. And let's see if I can just. Oh, isn't that pretty? Anyway, what is shown here in this horrible resolution is actually so our online acquisition branded paid search conversion rate, non-branded paid search conversion rate, and sort of our online acquisition total. So you can see that this is not exactly the example that I This is actually for a different country. This is for our Australia property. But I have just a massive amount of segments. They're high level, so it could be all of online acquisition, display, paid search, whatever, or very individual channels like branded paid search or non-branded paid search. So that is the Google Analytics portion. See if I can quickly show you RSiteCatalyst. So RSiteCatalyst is a little bit different. This package was developed by a guy named Randy Switch. Again, it's up on GitHub, but this one is on CRAN as well. So those of you familiar with RSiteCatalyst that actually care to use this, if you go into the admin console, basically you'll want to enable yourself as a data user, I believe it is. Give yourself those permissions, and you'll see in the console that you're actually given this thing called a shared secret, which I've just punched into there, and you put your property name and your login name, and you can go ahead and authenticate with that. It says authentication succeeded. And then, you need to get an idea of what metrics it is that you have available. Isn't that great? Not what I intended to run. So you can look at report suites. This will list all the report suites that you have, all the report suite IDs. And again, if you have data in multiple report suites over multiple countries, whatever it may be, you can quickly loop through these. This one is a little bit slower than Google Analytics, but still equally effective, I think. In this particular instance, for RSiteCatalyst, you're probably better off defining your segments within RSiteCatalyst, saving them, and then taking a look at them via one of the built-in functions in our RSiteCatalyst, and then just referencing them in whatever loop it is or apply function you want to do to sort of combine all these data sets together, write them to a text file, put them in a database, whatever it may be. So anyway, those were just two quick sort of toy examples of something which I think can be a big time saver for anybody who's doing web analytics on a regular basis. Cool.